startup Dreamfold. He's, as a PhD student, supervised by Joshua Benjo and Sarath Chandar. His research interests span generative modeling and probabilistic inference with applications to protein binder design. And he will tell us about the practical side of training GFlowNets.
Thanks, Kolya. Hi, everybody. So I'm going to talk about what Kolya said I'm going to talk about. So let's talk about it. Okay, so GFlowNets. GFlowNets are an interesting thing we've talked about. There's a lot of parallels, or there's a lot of connections between RL, generative modeling, and GFlowNets. These come in forms like Kolya mentioned earlier. There's deep connections between variational inference and GFlowNets. And in particular, the way we train GFlowNets is very similar to reinforcement learning. In reinforcement learning, right, we have an MDP. We take steps sequentially, and we get rewards over time. In GFlowNets, we do about the same thing. We have some MDP, something which is saying, at least in the discrete space, we have an MDP, something that's saying, from this state, I can take these actions, and I'm going to transition to these other places. And specifically at the end of an episode, at the end of trajectory, we get some reward. So generative models also not really like this. We train them very differently, but they kind of, in a way, do a similar thing, where you have data set instead of having not a data set. But you train them to match a target distribution. And specifically, in the variational inference case, you can recover some very similar things to what we do with GFlowNets. So as Emmanuel and Kolya already mentioned, there's really a core training loop of what we do for GFlowNets. So it's pretty simple. It's just like RL, right? So the first thing we do, we have some policy and we say, okay, policy, let's generate some experiences. So we get this batch of experiences somehow, and then next we're going to get some rewards. A GFlowNet is all about the terminal rewards, right? What GFlowNets do is they sample objects, as Emmanuel was talking about, proportional to the reward of those objects. And so these objects, we say, are basically the states we arrive at the end of a trajectory. So we generate our batch of experiences from our forward policy, and we get some rewards for the objects that these trajectories generated, and then we compute the loss on these trajectories. And so here, I'll make a quick note. This notation is a little bit different. I'm saying that we're sampling a trajectory from the forward policy, which is the same way as writing the same thing we had before. If we recall that a policy is a Markovian policy, then the likelihood of sampling of a trajectory is just the product of all the transitions in the trajectory. So this is the core training loop. Cool. Basically, the first and third part are very interchangeable. So Kolya was already talking about what do we do for step number 3. There's a bunch of different objective functions. All of these try to do the same thing in principle. We have a set of constraints for GFlowNets, and we want to try to say that everywhere in space, at all different times, these constraints are satisfied. Because if we do this, then we get what we want. We get a sampler that samples objects proportional to the reward. So that's one side of things. The other side of things is how do we actually choose, how do we get the data that we're going to use to train our GFlowNets? And so what we're going to focus on in this talk is specifically how do we get this data, how do we get the things that we're going to train our GFlowNet on? So how do we do this? There's 2 main levers. The first lever, as people have talked about, is how do we generate this data, right? So just like in RL, we have a policy, we simulate the policy to get back experiences. We can choose how we want to generate these experiences. We can change our policy, we can do different things to make it more exploratory, or maybe make it focus on specific modes more. And so we have ultimate freedom really to choose how we want to do this. This goes back to one of the core important things of GFlowNets, which is that because of the way the objectives work and the way the math works out, you can train them off policy. You can get samples, you can get data from wherever you want. If you train everywhere, you will get a sampler that does what you want. Of course, we don't sample everywhere, but the point is you don't have to sample as in VI, as in variational inference. What you typically, or what you might have to do is you generate things according to the thing you've already learned. And now if you want to go away from this, you have to import and sample, and this is sad. We don't want to do this. It's unstable. It's not as fun. But because of the way the GFlowNet objectives work, you don't have to do this. You can sample wherever you want, just as long as you try to satisfy detail balance or flow matching or trajectory balance or whatever other balance, you're happy. So this is one lever. How do we choose what, how do we design a policy? How do we get a policy that's going to help us discover modes, which is important, right? Like this, especially as you scale the problems, as you move the problems from, the toy, like real world tasks to really big real world tasks, right? Like the thing that I'm interested in is protein design. And for some of the proteins that you might want to generate, like they're say 200 lengths long and there's 20 amino acids. So how big is that? That's a search space of 20 to the 200th. This is hard to explore. It's just hard. And also there's other hard things, right? I mean, you could imagine having a very non-smooth reward functions, which is something that we want to do sometimes, right? Sometimes we want, what do we really want? Like if we're doing a search problem, we want to generate the best things, the best molecules or the best proteins or the best crystal structures. And we want to generate a diverse set of these. But to get the best ones, you have to sample, GFlowNets are going to sample proportional to reward. So you might have to make your reward function rather non-smooth and more peaky to try to sample more often the things that are really good. But the more peaky your distribution is, the more likely you might be to get stuck in modes and get mode collapse and be sad. So we should figure out a good way to do this. And we've done a bunch of things. The second thing is that now once we have the data that we've generated, how do we choose, even from the data we've generated, which things we actually want to train on? So this is stuff like Emmanuel was mentioning earlier, replay buffers. How do we choose of the data that we have, which things we want to use? And depending on the way we do this, you can see rather significant differences in how fast you train, but as Emmanuel said, with caveats. All right, so designing an exploratory policy. So let's say we have a target policy. This is our PF that we've talked about so far today. And this thing is like your normal GFlowNet policy, right? It's trying to, it's going to try to satisfy detail balance or trajectory balance, and it's going to try to sample proportional to the reward at the end of the day. So we can also have a behavior policy, just like in RL, whose job is just to generate samples that are good for PF to learn on. What do we want? We want something that learns the distribution. We want to be able to sample from R. So all we care about is, can we get a behavior policy, which is going to make learning to sample R as easy as it can be for the target policy? There's a bunch of considerations here, right? But one main thing is we want to try to have the behavior policy be, we call full support over the object distribution. So you can imagine if you do not have full support. So what do I mean? Like, let's say we have this grid here, right? And we have a behavior policy which ends up kind of saturating in some way, and it only samples the top left corner. If you show this to a GFlowNet, it'll be perfectly happy. It doesn't care. Like, it will see I can go to these 4 states. Okay, cool. I'll learn my Z and the trajectory balance to be the partition function for those 4 states. It'll learn PF and PB according to that partition function, and the loss can go to 0 everywhere, and the target policy will never sample anything besides those 4 states. So we don't want this. So we want to make sure we sample everywhere. And as long as we have some likelihood that we're going to sample everywhere, at least in theory, eventually we should converge to a true correct GFlowNet policy. Of course, this doesn't necessarily happen in practice, but in theory, it is true. Okay, exploration for GFs. Okay, obvious first try. What should we do? Let's just take the current target policy. But this is dumb. Don't do this. I mean, it could be okay, but like in general, it's not great. So, like I was saying, same thing. You could imagine you have like your current target policy isn't constrained to sample from everything. And so we see this happening here. We have this true distribution where it's very peaky. These corners, there's 3 corners that have some reward, and the GFlowNet's going to start from the top left corner. And it's perfectly fine for this GFlowNet to just go and find one mode. And you can pretty easily see, I mean, you can train this yourself and you'll pretty easily see that the loss goes to 0. But what happens is it just learns to generate maybe one of the modes. And even within the mode, it's not even capturing all the other states that are right next to it. It's perfectly fine to just saturate and mode collapse. And this is kind of expected. There's an interesting little proof in the GFlowNet and variational inference paper, which shows that if you learn specifically with trajectory balance on policy, the gradient you get is the same as the gradient of the reverse KL. And we know from generative modeling, this is not a good thing to do. The reverse KL has problems with mode collapse, and you see exactly the same behavior if you do on policy learning in GFlowNets, as you would in RL as well. So a second try, we can do some rather simple things that interestingly seem to work in many cases. So just like in RL, we can mix in uniform noise with the current policy that we're learning. So the most obvious example of this is to take an epsilon random policy, just like epsilon greedy in RL. And so we say that with likelihood 1 minus epsilon, we're going to sample an action from the target policy. And with probability epsilon, we'll just take a random action. The other version of this is really the way that we use GFlowNets in practice is that we, as many other things, learn the log its, and this gives us a Boltzmann distribution. And so as in other Boltzmann distributions, you can learn a temperature which controls how peaky or how flat this, this distribution becomes. And so we can use this temperature parameter, whereas if you increase the temperature, if you increase the temperature, the policy becomes more flat. And if you bring that temperature to 0, it becomes very peaky around the thing that it thinks is best. And so one approach is to just take a policy and take the logits that we learned for the target policy and temper the distribution with some like value of temperature greater than 1. To basically have a slightly more flat distribution than the target policy. And these actually kind of work rather like surprisingly well. Most GFlowNet papers use this to date. I mean, we've run experiments where at least in small scales, for example, in small scale settings, these work really, really well. Like it's hard to beat this, like in smaller scale settings. Even as you scale, like there's an interesting experiment we did at some point where we had, it was an RNA generation task and you have about 20 million states. So not near as big as, 20 to the 200th, but 20 million states. And with this exploration, the GFlowNet finds every mode that exists very quickly. But this has failure cases, as you might expect, specifically as the reward becomes more sparse. So like I was saying, if the reward basically becomes less smooth, or if the search space is very, very, very large, these things can start to fail. And so this is learning with a tempered policy on the same problem as before. And just as with an on-policy distribution or on-policy exploration policy, it mode collapses and goes to one thing. So how do we avoid this? We don't like this. This is sad. There's some ways to do this, right? I mean, you can imagine in this case, right? Like you could even game it with these, right? You could have a fully random policy. Like this would be fine. This would work. You could have a fully random policy, or you could bring the temperature very, very high, which people also do. This is a typical thing that people do in MCMC, for example, with replica exchange, where you have many different MCMC chains, all at different temperatures, and the higher temperature ones, higher temperature MCMC chains are more likely to sample everywhere in the space, and you can kind of mix these things. So there's a recent GFlowNet paper that is doing something similar with temperature, with choosing the temperature of the tempered policy. But there's other approaches that people typically use in RL, and we'll cover briefly 2 of these approaches. So first, something that's very useful in RL is to try to use intrinsic rewards to encourage exploration. So a paper in ICLR 2023 tried to do this with GFlowNets. And so basically, we use a pseudo count to augment the reward of the terminal state. And so basically, we change the reward such that for places we have not visited, the GFlowNet is incentivized to visit them more. And as it visits more and more, the reward goes down and the GFlowNet is less likely to sample this. So this paper in particular uses RND, which is a way to do pseudo counts in RL, and works rather well, specifically when we have a very sparse reward. So here is, this is 2 results. On the left, they take a very, very sparse grid. And in this case, the this sort of intrinsic reward approach works very well. Very similarly for molecules, they use a sparse version of the molecule task. This also works very well. There's other things you can do, right? Another RL exploration paradigm is to use uncertainty, and there's much work on this direction. And so this also works in some cases if the search space is very large, or if it is sparse as well. And so what you do here is very much like bootstrap DQN and RL. You keep a ensemble of policies. At each step, you choose a member of the ensemble and generate a trajectory according to this member of the ensemble. You can encourage diversity in multiple ways in the ensemble with bootstrapping or prior networks. But this is like, these are 2 versions of these things. This is a general recipe, right? Exploration for GFlowNets isn't that much different than an RL. There's many ways to use uncertainty to give better ways to explore in RL. There's many ways to use intrinsic rewards. There's many ways to do exploration besides these things in RL. These are all things that probably will work, probably will be very useful. They haven't been tried. And so if people are interested in this, they should try. These are good things to try. So yeah, if the exploration problem is a bit harder, if the distribution is maybe not so easy to generalize to, for example, Thompson sampling works well. There's other things we can do. Say we have a data set. Say we know some really good samples. We can take one of these really good examples, X, and we can simulate we can sample a trajectory from our backwards policy and train on that trajectory. And this has been very useful in a bunch of different papers from back in 2022 on energy-based modeling with GFNs, doing EM with GFNs, also doing things for making exploration better with MCMC. This also works there, where, for example, you take something that is close to a mode, you do a small chain on it to get a really even better sample, and then you train on the backwards trajectory that you get from those very good samples. And like I said, you can also play with tempering the reward distribution, as in replica exchange, for example, or the temperature conditional paper. So what things should you do? It's the first rule is just don't do one policy. Like, this is just don't do this. But besides this, it's not so clear. You just start, basically, I think the easiest thing to do is just start out with epsilon noisy or tempering. This works for a lot of settings. Like, it really works for a lot of settings. For things that are getting harder, you might need to start being a bit more smart. Maybe try something like JFNs or Thompson sampling. Or if you're feeling brave, try your own new like uncertainty method or intrinsic reward, or take something off the shelf from RL. It might work. If you do have a data set, you should use it. Mixing and training trajectories sampled from backwards policy is quite powerful and is very useful if you have access to samples, which in some cases we do. All right, so that is exploration. Now, what is the next thing is we have data. We've generated a bunch of data from our exploratory policy. How do we choose what data we're actually going to train on? So let's say we generated a batch of trajectories from our behavior policy. How do we choose which of these trajectories to train on, right? So there's been a bit of research into this, and right now there's basically 3 options. The first is just don't use a buffer, just take the batch of trajectories, train on it. Second, that people do commonly is take a standard like uniform first in first out buffer as an RL. And the third thing that people have done is take, again, a first in first out buffer and try to prioritize based on reward. People have also tried a bit prioritizing based on the loss, but I think the results on this are a bit less well-founded at this point. So reward prioritized buffers. This is from a paper with Emmanuel and Nikhil, and also in a paper with Andre Nika from 2022. And so here the idea is we have a batch, or we have a bunch of trajectories and states in a buffer, and we can try to prioritize those states which have higher reward, and train on these more than other things. And so the specific scheme that most of these reward prioritized buffers have done is basically take the top alpha quantile of rewards or objects with rewards in the buffer and choose beta % of your training batch from this and 1 minus beta % from the rest of your buffer. There's other ways you can do this. You can just sample proportional to the reward in the buffer. These things also can work, but this can be pretty useful. Specifically, it's been found in, for example, Emmanuel's paper that basically if you do this, you will converge to a good value, perhaps faster. And in some of Nikhil's work that you can discover more modes, but it does come with caveats, right? You have to be careful with how you're doing this. If you do this naively, if you make it too, in a sense, greedy, choose too much, too big of a beta, or make the top % too small, say you're only training on the top 0.5%, you can run into a very myopic policy. You can end up with mode collapse again. And so there are things you can do. You can try to, you could try to add in some measure of diversity in how you're doing this, maybe in your insertion strategy or in your sampling strategy from the buffer, or you can just play with the hyperparameters, but you have to be careful. I mean, imagine, right? Like if you're just choosing the best things, you're just going to keep choosing the best things and you might mode collapse. So this can be very useful for training. Just make sure you're not doing the wrong thing. Just make sure the things you're doing or the results you're getting are making some sense. Okay, so wrapping up. For exploration, what should we do? Steer away from doing on-policy learning. Start with just simple exploration things, just like in RL, do epsilon noisy and tempered things. If this doesn't work, try out more RL-like exploration methods like GFlowNets, which try to do intrinsic rewards, Thompson sampling, which tries to do uncertainty, or genuinely you could try many different RL things that people have done for uncertainty, and it may work out pretty well. For replays, uniform buffers don't seem to help all that much. There's been some results on this. I think just in general, people have not seen a huge difference between just using a uniform buffer, just you doing a uniform buffer versus just training on the batch of trajectories you've generated. Perhaps if you try to add in some things around diversity, you might get some better making sure you're not like forgetting modes. But just vanilla uniform FIFO buffers don't seem to help much. But prioritized buffers do seem to help. So try them. Just make sure you're not doing something that's making your policy die. So yeah, happy training. A couple quick helpful things, just small things that can make a big difference that are not related to exploration or replay buffers. So stabilizing learning. This can be a big deal, especially as your rewards become very big. So for example, if we want to do search, we want to make some of our rewards very big, especially if a very big search space, you have to do it. Otherwise, you just won't sample even if your GFlowNet converges to the right thing, it won't sample what you want. So you, in some cases, just need to make your reward very, very non-smooth for search to work. And so in these cases, you can start running into issues with stability. Gradient clipping is critical on some problems. You might have to play around with hyperparameters. Using delayed network can help training. So using EMA on exponential moving average on model weights can be useful. There's recent work on target networks to help stabilize things, and so on. Another thing that I forgot to put on here, and I'm just remembering, normalizing the reward, making sure, trying to get your reward into as nice of a scale that you can under the constraints that you have can be quite important. And another trick we've found that can sometimes help a lot when specifically you have a very low reward temperature T. So this means basically your reward is going to be very spiky because you're dividing reward by this temperature, right? So maybe it's 1e-5 or something. And so it means your reward gets very spiky. Rescaling the loss by the temperature to some exponent, maybe 1, can be critical for not making everything blow up. So yeah, that's it. If people have questions, I am happy to answer them.
I have a question about the exploration strategies you talked about. You briefly mentioned count-based exploration and random network distillation. Usually these techniques assign a reward at the current state, but for GFlowNets, we only assign rewards at the terminal state. So my question is, if you have a trajectory, do you estimate that exploration reward along the trajectory, or just the terminal state, or at every state and then for propagated?
You can. Actually, in the GFlowNet paper, one of the contributions is to be able to use intermediate rewards and help this for sampling. So you can do this. It might help your problem. I think it's problem dependent if it helps versus even just using the reward or count-based exploration on the terminal states. But you can do this. If you're interested, check out the GFN paper.
Thank you.
Mm-hmm.
I was just wondering, which methods would you prioritize in a situation where you know in advance that all the trajectories you have available for training start wrong?
Something exploratory, I suppose. Something exploratory. I mean, you could start out with something with a very large value of a very exploratory epsilon noisier tempered policy. You can, I mean, all these exploration things have hyperparameters that control how exploratory they are. Like I would start with higher, and you can always anneal your exploration parameters down as you go. Like, so start high, be exploratory, and then.
Hi. Like when I think in this slide, in this session, like you assume that reward functions are kind of known, right? But
Yes.
let's say like reward functions are unknown and we need to learn from data. In that case, like should we add more bonus term, like coming from a certainty of like unknown reward functions?
That's an interesting question. I'm not sure I have a good answer. So you mean like inverse problem settings, or are you thinking in like energy-based modeling settings where you're trying to learn an energy?
I'm just considering a kind of setting when the our reward is unknown and we need to learn from the data.
I think it's not, at least to me, it's not clear. I would say try things. Try a bunch of different values. Maybe Kolya seems like he might have an idea. Yeah.
If I may make a little comment on that, I've seen a few settings where you learn the reward, either because the reward is given by likelihood under a generative model or as an energy-based model, where your estimate of the reward function starts out really smooth. And when the reward function starts really smooth, it's easier to learn the policy to match it. And as the reward function evolves and becomes spikier, it becomes harder to explore. And in this setting, actually, exploration is a lot less important because it's easier without exploration to match a very smooth reward function. And as the reward function becomes peakier, you gradually settle into the modes. But I suppose it always depends on the specific problem at hand.
Great.
Can I ask another question? Like, I remember that so like there's a kind of analogy for like Q-learning and also like flow matching objective, right? And are there any like the similar concepts to like which are analogous to like a policy gradients stuff?
I think there is actually a very recent work. Somebody else might be more familiar, but I think there was a recent work submitted to iClear maybe on policy gradient with GFlowNets. I think there's recent work on this. If you look it up, it should be around.
Okay, thank you.
Thank you, Jarrid, for the talk. You mentioned earlier that there was this connection between TB and reverse KL. Is there a similar connection that you're aware of for replay buffers between a different divergence?
Different averages?
Different divergence, like for example, I don't know, like that it's not purely like a reverse scale anymore, right? It would be like some different divergence, maybe like a mix between forward and backward, or some maybe.
Yeah, we've thought about this a bit. I mean, I think so, right? I mean, you can imagine you try to do importance sampling from your buffer, and then you could say, I have the forward like KL, but then of course you have to importance sample. Like, there might be interesting ways to. Maybe Kolya has thought about it. We can talk about it after. There might be interesting ways to try to think of like other divergences besides, something where you have to importance sample. Maybe you do have to importance sample. I don't know. I think I have tried at some point some importance sampling experiments, but I don't remember what happened with them.
Thanks.
Yeah. Cool. Great. Well, thank you, everybody. May you train GFlowNets well.